As Bill said, my name is Vince Fuller. I've been doing this internet operations stuff since before the dawn of time. Jason, fortunately, is a little younger and is not doing this quite so long, but he seems to be becoming cynical just as rapidly as possible. Anyway, what we're going to talk about is some thoughts we have on ipv6 and actually more importantly the subject of multi-homing and scalability thereof for the internet in the future. I'm going to talk about some of the history behind how we got to where we are today. I'm also going to talk about some conceptual things. Some of you may have seen some discussion on the Architecture Discuss list or on PPML or on NANOG or on a number of other places over the last year or so where people have talked about the concept of locator and endpoint ID as distinct from what we now think of as addresses. I'm going to talk a little about why this is important, why you might want to think about this, and why the community needs to think about this going forward. Look at what the situation is today with IP version 4 and IPv6 and why it kind of mingles these two concepts together and why that's a problem. And then sort of look at where we think multi-homing will go and where routing scalability will go if the current trends continue. Finally, we're going to solicit some interest from this group and from others in the community for whether we should do some work on an alternative direction for the internet routing system. Okay, brief history of time, paraphrase a famous book title. This is kind of how we got here. Sometime during the late 80s or so, we started to see wide-scale commercialization of the internet. That led to the exponential growth that we all know and love, that created all the jobs for all of you folks sitting here in the room today, and keep us all nice, well paid and comfortable. Unfortunately, the growth sort of started putting some stresses on what had originally been a fairly small network design that was never expected to go to become a ubiquitous global infrastructure the way it is today. This recognition of this growth and some disturbing trends started in the late 80s. And there were a number of approaches that were taken to try to deal with this. First was an edict that came down that TCP/IP would be replaced by the OSI protocol stack, in particular TP4 over CLNS. You've probably never even heard of this bit of gobbledygook because it never went anywhere. There was something of a revolution against the self-proclaimed leaders of the internet community at the time, and that whole proposal was defeated. Again, in the early 90s, there was a small group of people that got together to try to solve this problem. Some pretty smart brains looked at this. I happened to be along to take notes. Don't really fall into that category. But they identified three problems that were looming for internet growth and stifling thereof. The first was running out of Class B networks, something that we don't even talk about anymore, because that problem was actually solved. Originally there were three types of network sizes, /8, /16, and /24 is what we call them today. And the most popular one was the Class B, because just like with Goldilocks and the Three Bears, one was too big, one was too small, and the third was just about right. So everyone wanted that. That problem was solved, but the other two problems, ongoing explosive growth, well, that one was sort of deferred. It was dampened for a time, but now it seems to be coming back to bite us. And the eventual exhaustion of the 32-bit address space was not really a critical problem in 1992, but it's starting to become a real possibility today. The result of the road group was two efforts. One, a short-term effort that evolved into what we call CIDR today, and the other was a long-term effort that has sort of turned into IPv6, for whatever that's worth. There's a whole gory description of this process at this kind of obscure-looking URL that I found by doing a Google search. And for those who are interested in internet history, I encourage reading it. Following the adoption and deployment of CIDR, which was a rather politically painful experience that some of us had to endure, there was a solicitation for an IP next generation protocol stack. December 1993, RFC 1550. Subsequent RFCs described what the technical criteria were supposed to be for selecting this, and 1,000 blossoms bloomed in the form of different proposals from people, ranging from Tubo, which essentially was re-implementing TCP over CLNS-style addressing, to other things that were more innovative, like PIP, which was sort of roughly analogous to MPLS or other source routing techniques, and Nimrod, which was actually sort of a architectural description of how you would deal with this problem at a higher level without really looking at the details of how you'd implement the protocols. A lot of discussion, a lot of flaming back and forth, a lot of heated arguments and anger toward other evil factions in the community. The choice basically came down to politics rather than technical merit. And when I think back on these times, sort of the image that immediately comes to mind is that of one of these talking Barbie dolls that my little sister had back in the late 70s, where you pulled the string on the back and the Barbie doll said something. But one of the things the Barbie doll said, which is entirely non-PC today, was, "Math is hard. Let's go shopping." That's kind of summarizes what happened with the whole IPv6 decision process. Solving multi-homing, looking at difficult problems was hard, so people decided to design packet headers instead, because that was easier, more fun, and you got to attach your name to a standards track RFC, so it was really cool. Anyway, because of this process, a lot of things got lost in the shuffle. The concept of variable length addresses was discarded. Decoupling of transport and network layer addresses was considered problematic for several reasons, so it was discarded. And most importantly and most fundamentally, a clear separation of endpoint ID and locator was either ignored because people didn't understand the concept, or because, again, it was hard and we wanted to go shopping instead. And then this, of course, led to some issues with route aggregation and abstraction, which we sort of kind of shuffled under the rug under the guise of let's just do CIDR from now on. In fairness, these are hard problems. They were hard then, they're hard now. But if we don't solve them, we're going to have some pretty serious scaling issues that we have seen for the past 15 years with IPv4, kind of suppressed and solved in a short-term way, but we're going to see in a much bigger context going forward if the internet does become as ubiquitous and wide-scale as we expect it to. Anyway, stepping back and talking conceptually a little bit, just want to say a few brief words about what the whole concept of endpoint ID and locator are. Again, some of you may have seen some of this discussion, and I don't have much time, so I'm going to make this quick. Endpoint ID is basically the name of one endpoint in protocol exchange. Could be a process, could be a machine, something that terminates a TCP session at one end to another endpoint at the other end. The analogous thing in the real world is a name, like Dave Meyer or Bill Woodcock. It's who is involved in the communication. You can think of a domain name as sort of being a human-readable version of an endpoint ID, although domain names can also be kind of abused for other purposes. Endpoint IDs have a number of desirable properties. Persistence, once you set up a connection between two endpoint IDs, you don't change the endpoint IDs. So a session can stay, up forever as long as the two machines are up and as long as there's communication that needs to occur. It's nice if they can be administratively assigned, because they tend to be assigned to organizations and by organizations to their subparts. So the hierarchy for endpoint IDs is generally along organizational or a grouping of similar organizations rather than anything having to do with network topology. IDs are ideally entirely portable. They stay the same even if an organization moves from one part of the planet to another, or if it changes the number and set of providers that it's using. And they're globally unique. That's one area where the analogy with human names kind of breaks down. But a human name is human identity is more than just their name. A name is sort of a shorthand. The other concept is locators. Locators essentially states where a device or process is located in the network. The source and destination addresses that you use in routing and forwarding today, well, those are locators. The real analogy here is a street address, which can be specified to fairly high precision, but doesn't have to be once you're far enough away from the destination where all of the more specific information kind of looks the same to you. You want the hierarchy associated with locators is generally along topological lines. Ideally, it is completely along topological lines. In other words, number, street, city, state, country, or in the case of the historical phone system, prefix and area code. I realize that has all changed since then, and actually there are some things to be learned about internet address portability from the phone number portability experiments of the last decade or so. Locators have a number of desirable properties that aren't really the same as those of identifiers, and herein is where we get into some issues. Again, the hierarchical assignment is according to the network topology. To use a fancy mathematical word, it's isomorphic. Dynamic transparent renumbering is possible without disrupting any transport layer sessions. In general, locators are expected to be unique when they're fully specified, but you can reduce the precision of what a locator covers to reduce the amount of state and thus improve the scaling of the routing system. Variable length addresses are one way of doing this that, again, the Internet architecture did not follow, and less specific prefixes are the way we kind of deal with this today. You have a /32 that specifies an exact IP address, and then you can summarize that up at various levels by shortening the prefix in the routing system. The real-world analogy here is that you don't need to know the exact street address in Australia if you're traveling toward it from San Jose. Or to follow the song, you don't need to know the exact address of the convention center in San Jose if you want to know the way to San Jose. Locators are possibly applied to traffic without the end systems really knowing what's going on. So there can be a little bit of smoke and mirrors that sort of is like NAT, but you don't really break the sacred end-to-end principle, which tends to get a lot of people up in arms when you do. Why do you care about this? Why should anyone care about this? Why should anyone stop reading their email long enough to listen for 5 minutes? In ipv6 and ipv4, there are only addresses, which try to serve the purpose of both endpoints and locators. And as when someone tries to serve two masters, they usually don't do a very good job of either. This means that they don't have the desirable properties of either. Assignments to organizations is painful because use of locators constrains them to be topological. In other words, the so-called provider-based addressing, which really isn't, I mean, provider-based addressing is really topological addressing to make the routing system scale. But because providers dictate, well, they build the topology, the assignment tends to be along those same lines. Exceptions to topological assignments create additional global routing state. This is a problem. This is why multi-homing is such a big issue. This is one of the main reasons why the routing table has grown to 180,000 plus globally visible prefixes today, even though topologically the network really isn't that complicated. Renumbering is hard. DHCP doesn't really do everything for you. Changing addresses disrupts sessions. This is actually kind of an interesting key point that was missed in the design of IPv6, that by embedding all of the full IP address in the TCP header, you basically make it very difficult to change addresses and do any kind of renumbering without disrupting sessions. There are other issues. Weak authentication is used. Source-based filtering, makes it difficult to do renumbering. There's a whole raft of reasons why renumbering gets difficult when you're commingling locators and identifiers. And basically, the fundamental issue is that you can't make the routing scale for large numbers of provider independent or topologically independent addresses, aka multi-home sites. Again, why do we care? Well, right now, particularly looking at the IPv6 forwarding table, you probably don't care because the forwarding table is a few hundred entries. It doesn't really fast, but that's true of any prototype network in a lab or in an early adopter stage where you haven't started to see a serious growth curve. If it does really get adopted and you don't solve this problem, you're going to have routing state, growth of routing state that becomes rather ugly rather quickly. The larger IPv6 address space gives you a lot more potential for more specifics and other things to make the routing table bigger. Today, by doing that, you're effectively implementing an ID locator split. It's not a very clean or very elegant method of doing it, but it's effectively what you get with NATs. If you get rid of the NATs, which is what all the IPv6 proponents would like you to think is nirvana, suddenly all this hiding of state goes away and you get even more growth of the routing state. Again, the scale of the IPv6 network is tiny, and even the scale of the IPv4 network is relatively small compared to where it could go in the future. If we start thinking about personal area networks, multi-homed individual residences, things of that sort, the scale of the network gets orders of magnitude larger than it is today. And the bottom line is that recreating the routing swamp with IPv6 and much longer addresses is probably not a very good idea. It's somewhere between not a very good idea to disastrous on the scale of what will happen to the routing system and the people that have to manage the routing system. Unfortunately, this problem, again, it's a hard problem, and we'd rather go shopping. It's been ignored for the last 10 plus years. And not only has it been ignored for 10 plus years, but the concepts behind this have actually been known for a lot longer than that, probably on the order of 30 or 40 years, given that some of the papers in the additional reading section date back to the 60s. Can IPv6 be fixed? And what's this thing that you might have heard of called GSE? Basically, GSE was a way proposed by a smart guy named Mike Odell back in 1997 to take the existing IPv6 protocol stack and addressing architecture and retrofit in a method of doing endpoint ID versus locator splitting. Basically takes the IPv6 address, splits it in half, uses half of it for routing, uses the other half for endpoint ID. Again, with a nice Google search, you can find a reference to the document that he wrote in 1997. It's actually a pretty interesting reading, and I highly recommend it. The problem with doing GSE is that you have to make a few changes. In particular, when I mentioned that using the addresses directly in the TCP header makes it really hard to renumber things. Well, when you do GSE, you essentially have to fix this problem. You have to go back and make incompatible changes to TCP and to UDP so that you don't do that anymore. The whole point of this is to allow for the routing system to modify the routing goop, to use a technical term, on packets in flight and arbitrarily according to the routing system without having to touch the identifier portion and without the host having to know about any of the magic that's going on behind the curtain. Again, we want to keep the locator system isomorphic to the network topology. GSE benefits. Achieves the goal of locator split, locator ID split, while keeping most of IPv6. For those who think IPv6 is a wonderful, valuable thing, this is a benefit. It allows or facilitates scalable multi-homing by allowing a different routing information to be assigned to multiple paths to an end system. In some respects, it's similar to the way that Shim6 works in this here, in that there are multiple addresses associated with endpoints, but the hosts don't need to know about that, so it reduces a lot of the complexity and some issues with the hosts. Again, unlike Shim6, it does not require some of the transport layer complexity for doing address detection and such, and to deal with multiple addresses. Renumbering can be fast and transparent to hosts with no need to detect failure of unusable addresses. Issues, problems open with GSE. Well, again, there are incompatible changes needed to TCP and UDP. Back in 1997, there was no installed base of IPv6, and there was seen as plenty of time for transition. Well, some people would argue that today there is a huge installed base of IPv6 that would be severely impacted by any change to the protocols. Therefore, protocol changes are impossible. But looking forward, the number of installed hosts is actually pretty tiny compared to what it's going to be in 5, 10, 20 years. Some purists would argue that there's a violation of the end-to-end principle. There are perceived security weaknesses, in particular, because endpoint IDs can be used to route traffic to hosts independent of the routing system. This opens the door for a new class of what is seen as a new class of attacks on hosts that actually turn out to be attacks that already exist that just aren't that common. Steve Belvin, sitting in the back, says that this problem can be worked around, and I trust his knowledge of security far more than my own. Mapping of endpoint ID to endpoint ID plus routing information may add complexity to the DNS depending on how it's done. This is all something that needs to be looked at, and yeah, there are probably some issues here that need to be resolved. Traffic engineering, which is kind of the popular subject and one of the reasons people hate Shim6 in this community, was not considered in the original design for GSE, so there would have to be some work on that. It may involve doing traffic engineering somewhat differently than it's done with IPv4 today, but pretty much any scalable implementation of routing is going to have that property. And the biggest problem is that nobody's looking at this. The draft is expired. It was basically killed by IETF politics some years ago. One thing to note is that GSE is not the only approach. It's just one. Again, the goal of GSE was to keep as much of IPv6 as possible, but with still retrofitting in the endpoint ID locator separation. There are other ways of skinning this particular cat, such Nimrod being kind of the classical, the architectural approach to doing full separation, but Nimrod is not entirely specified. All these proposals have issues associated with them, but the biggest issue is that none of them are being pursued. Okay, what about this Shim6 stuff you've probably heard of? It's about 3 years old. Basically, it involves giving multiple addresses to all the multi-home systems and hiding this all behind a shim that makes it look to the host as if there's just a single address. There's all kinds of, I'm kind of running out of time, so I won't go into the details, and the details are available elsewhere in much better technical description. There's all kinds of complexity involved, and there's all kinds of issues involved in how you hide what's going on from TCP, how you make it all work when addresses come and go, when links fail, etc. There are some issues with shim6. Nobody seems to like it. That's the biggest issue, and different people dislike it for different reasons. Service providers don't like it because you can't do traffic engineering. Hosting providers don't like it because that adds more state to their servers. And end sites don't like it because they still really don't get provider-independent addresses, which is what they want. So they still have to renumber in some cases. Will shim6 solve your problems? Well, judging from the feedback we got at the last nanog, doesn't seem like it, but I'd be happy to be convinced otherwise. What if nothing happens? What if we don't do anything about this problem? I've done a little thinking about this, and I launched a little bit of a discussion on a couple mailing lists a few months back that takes a few assumptions about IPv6, internet growth going forward, and guesses at some of the growth trends, and then asks some questions about where we think things are going to go. Jason actually has some detailed numeric projections of this based on some even more sketchy assumptions, but it kind of gives you an idea of what we think might happen. What's the worst case? What do vendors have to expect to build, and what do providers have to expect to deploy, and how quickly? A few assumptions behind this. I don't agree with all of them, but they're assumptions that kind of are looking at what we could do without changing a whole lot of the current direction. First assumption is that IPv6 will be deployed in parallel to IPv4 and will be widely adopted. There's some reason to think this might happen. There's some reason to think that might not happen. But if it is the way forward as dictated by the IETF and company, then I guess it has to happen. In the short term, IPv4 will be the predominant protocol and will continue to be used indefinitely. This is kind of important because it means that you need to carry both IPv6 and IPv4 routing state for the indefinite future. Routing state growth, particularly that for multi-home sites, will continue to grow at a greater than linear rate. In other words, exponential or quadratic, up to or beyond address exhaustion. What I mean by beyond address exhaustion is that as the IPv4 address space runs out, it will get increasingly divided up into smaller and smaller pieces hidden behind NATs. But increasingly smaller prefixes will then start being routed uniquely as they become topologically diverse parts of the network. As a consequence of this, routers in the default free zone, quote unquote, will need to maintain full routing and forwarding tables for both IPv4 and v6. Tables will continue to grow, and there will be significant churn over time, going forward. A few more assumptions. Prefix assignments will be large enough to allow most, if not all, organizations to aggregate all of their addresses into a single prefix. This means this is actually a good thing about IPv6. It means you won't have providers that have 20 prefixes that have to be 20 different routes because they couldn't get a big enough block initially. I don't think shim6 is going to see significant adoption beyond residences or extremely small businesses, extremely small organizations. And IPv4 style multi-homing will therefore be what we do going forward for IPv6. Am I running out of time? Yeah. I'll skim through this. Blah, blah, blah. More multi-homing, traffic engineering will be IPv4 style. Other things like AS hop count won't significantly reduce state because they're too hard and they're knobs that are just too difficult to implement and just point solutions. Questions to worry about is how much routing state growth is due to organizations needing multiple prefixes. This is one of the things that IPv6 will fix. Will the number of prefixes and the growth rate tend to decrease towards the number of ASs. In a perfect world, if every organization had exactly one prefix, the number of prefixes would match the number of ASs. Traditionally, in the IPv4 world, the ratio of prefixed AS is about 6 to 1. What will it be with IPv6? 1 to 1, 2 to 1, something else? Probably not 1 to 1. How much growth is due to unintentional more specifics, which can be avoided with an intelligent deployment and design? How much of it is due to intentional more specifics, such as traffic engineering? These things are also going to happen with IPv6 because we really don't have another way to do traffic engineering and other stupid pet tricks in the internet today. What's the churn rate? In other words, how fast does your CPU have to be to deal with all of these updates and withdraws? What happened? And then one of the questions that Jeff asked is, what happens if we add more state to the routing system so that, for security and such, so that the CPUs are even more heavily loaded? Jeff did a projection of this and a report on this back at Apricot, and then again, I guess at IETF Grow, that kind of looked at some of these numbers. They're kind of disturbing. I won't go through all of them in detail, but it's starting to look quadratic or exponential again, and that's bad because it's really hard to keep up with growth rates quadratic or exponential, even if you start out with a small number of objects. The classic example is taking a penny and doubling it every day. By the end of the month, you're a millionaire or a billionaire. Well, we're going to have millions or billions of prefixes if we keep doing things exponentially. Jason, actually, I'm going to give Jason a few minutes here to go over his analysis. I hope that's okay, Bill, if we take another 5-10 minutes. And then I'll do a quick summary at the end.
Keep it closer to 5, though.
Okay. So, Ron.
All right, so let me try and kind of run through this really quickly. I don't really want to talk about when V6 adoption is going to happen. Go ahead and debate that. The assumption basically is that V6 widespread adoption will happen, and what will the routing table look like when it does? In other words, what does it mean to make a long-term commitment to do deaggregation in IPv6? The way in which I do this is I look at the V4 routing table and try and project what the V6 routing table would look like. And in the V4 routing table, I try to identify 3 different types of routes. Aggregates, deaggregates that are because you've got 2 non-contiguous blocks, you got a /24, you grew out of it, you got a second /24. And deaggregates that are for traffic engineering. For example, you have a /20 and you break it up into multiple /24s for TE. And the numbers I'm basing this on is the Tony Bates CIDR report, where it says the number of prefixes and the number of CIDR aggregates that could easily be reduced down to. If you take the difference of these 2 numbers, you can assume that these are all of the intentional deaggregates that are used for traffic engineering, in this case around 61K. So what would the routing table look like, assuming we were doing dual stack and it was widespread adoption? You start off with your 180K V4 internet routes. You add to that your new IPv6 routes. You have to have 1 aggregate per AS. There's 21K active ASs in the routing systems. That's another 21K. You add to that your intentional IPv6 deaggregates, which we measured from the Tony Bates CIDR report to be around 61K. So that's your internet routing table. On top of that, you have to add your internal more specifics. For a Tier 1 ISP, that's somewhere between 50 and 150K. And your V6 internal more specifics, which we projected to be somewhere between 40 and 120K. And this adds up to a fairly large number today, 530K routes, which is not easily done in all boxes that need to fill packets in hardware in order to be able to forward 6 million packets per second. There are a couple of things that this interpolation doesn't account for. It does not account for a single AS that currently has multiple non-contiguous networks. But if they were given a single contiguous network, would still make multiple announcements. For example, a single autonomous system that is 2 stubs that connects to an upstream in 2 different locations using 2 different /24s. If they got a /23, they would still announce 2 /24s. It also doesn't account for all of the ASs that have just a /24 and make a single announcement. In the V6 world, if we give them a /48 or a /56, is it likely that they will try to put more specifics into the routing table because they can? But in the V4 world, the /24 is the smallest, typically the smallest routable space, so they can't divide that up any smaller. The third thing it doesn't account for is people that have multiple NAT addresses and they're hiding a service behind 1 or more NAT addresses. In the V6 world, it seems unlikely that NAT is going to be useful because of the number of addresses you have. So if they're using that for a TE mechanism, they're likely to need something else. And lastly, the big one, which is a huge unknown, is all of the new V6-only networks that are likely to pop up. You know, whether we're talking about China or cell phones or coffee makers or toasters or RFID IDs. There are a lot of people that think that because there are a lot of addresses in V6 that we need to put an address on everything, and that could have some impact. So just go through a couple graphs real quickly. The first one you see here is on the top is your V4 routing table in red. There's some projections. The best fit looks to be quadratic. The purple line below it is the intentional deaggregates. Its projection also seems to be quadratic and much steeper. If you add this is the number of active ASs, which seems to be fairly linear. If you add the two of those together, your active ASs and intentional more specifics, you get a projection of what the V6 routing table is likely to look like. I also looked at internal more specifics for V4. There's two lines here. The top one assumes you're around the 150K mark. The bottom one is if you're around the 50K mark. This is based on the growth of internal more specifics at UUNET, and their projections are quadratic. When you add it all together, you get some fairly large numbers. So if you're looking at, say, for a 5-year number on the low side, we're looking at 650K on the high side, 1 million routes. At the 10-year number, 1.1 million on the low side, 1.8 million on the high side. There was some discussion on PPML about, are these numbers ridiculous, and what are some other methodologies to look at this? And Marshall Eubanks had some interesting comments about the number of multi-home small businesses that might be likely to happen in the U.S. He found a number of 1.2 million companies with 10 or more employees. If these are all likely to be multi-homed, and you make the assumption that the U.S. is 1/5 of the global economy, that suggests about 6 million multi-home businesses. If they're all announcing just one aggregate into the internet routing table, that's 6 million additional routes. If instead we think that they're going to advertise more specifics for traffic engineering, if they're going to do maybe 8 per business like they do in V4, then it's a much larger number, 48 million. If it's maybe more like 4 if you take out all of the non-contiguous, non-overlapping space, then you're still talking about 48 million. It's kind of an interesting number.
Actually, this is one of yours, I think, isn't it?
Oh, is it? Yeah.
Yeah.
Yeah, so the short of my conclusion is I basically want to make sure that we understand what it means to commit to long-term routing table growth. Is this a problem we really want to sign up for? Do we want to continue to ask our vendors to build boxes big enough, and we need to build them big enough, long enough for us to be able to test them, deploy them, and have them live in the network for some time? 5 years is the magic number in our network. So the question really is this the problem we want to have, or do we want to find an architectural solution?
And one comment I'll make before I hit the last conclusion slide is that as a vendor, this is actually a really good scenario. Back in the late 90s, people were having to turn over the networks and buy new routers every 3 years, and Cisco cleaned up. That's why it became one of the largest growing companies during that period of time. So from a vendor perspective, bring on the growth. But from a long-term user perspective and community perspective, it probably isn't really the best approach. Anyway, in conclusion, is there a real problem here, or are we just a bunch of chicken littles running around looking at the sky falling? Does this problem need to be socialized elsewhere, not only in NANOG and the other operational communities, but other places where solutions might be sought? Tried this in the IETF. The IB IHGA is actively hostile toward this work because IPv6 is the one way, and Shim6 is the way to get there. NANOG, RIPE, Apricot, there's been a little bit of effort to socialize it there. That's what this talk's all about. Should we go to the ITU? That's been the enemy of the internet community for all these years. Your favorite router vendors, research community, other suggestions, we're open to hear it. Again, there's been some discussion earlier on the architecture discuss list, on PPML, and a little bit on NANOG. And if you're interested in actually working on this problem or in following what's going on, I created an alias that is, for right now, just a contact point to solicit interest. So I encourage you to send mail to this alias if you're interested in this subject. Bunch of recommended reading. I'll leave it here in the presentation. You can go through it later. I guess we have, 1 or 2 minutes for questions? Or
So we're 10 minutes over time right now into the lightning talks. There is supposed to be 1 hour of lightning talks and then a half-hour break. So at this point, if we're going to do all the lightning talks, we're 10 minutes into break right now. Sense of the room, do we want 5 minutes of questions?
looks like
We've got
5 minutes worth of people asking
at least
questions.
5 minutes of people. Okay, so all right, let's do the next three or four questions, really fast questions, and we're running into break now.
More of a, hopefully it won't be lightning striking me from the sky, but Steve.
Yeah, I'm Steve Bellevin, Columbia University. Just a couple of clarifications, and I've liked locator ID separation since literally 1986. A lot of these things were seriously discussed in the IPNG Directorate, which I was a member of. The issue is that there was no really well-formed, fully worked-out proposal for how to do it.
Yep.
And we had advice from people like Vince Cerf, who said, we tried this way back when, and it was a lot harder than it seemed. My comments on security had to do with authentication,
Right.
not denial of service, where there's still some open issues. So it's a lot harder than it seems. It's a good idea. We want to go there, but it's a lot harder than it seems.
And I agree completely. The only reason I invoked your name in that context was that when we discussed this on the mailing list, you said that there were no fundamentally insurmountable issues here.
That's still my take.
But there absolutely needs to be more work on this, because none of this stuff is thought out beyond the conceptual stage at this point.
Yeah, it was not quite as much ignorance of the issue in the IPNG Directorate as people might have gotten the impression, is my point.
Okay.
We really did consider it.
Thanks for the clarification. Randy.
Randy Bush, IIJ. We've been discussing this for a little while now, Vince, and flip back one slide.
Should I put my Don Quixote slide up on the screen?
Where do we talk about it? It's a moot question. We've talked about it everywhere. The problem is the people who need to do the work, and they're all burned out because
Yep.
of the denial and because of the stonewalling at IETF, et cetera. So we, the operators, wearing other hats, are going to pay for this and be caught in the long run. V6 is barely deployed. Thank you, Alain Duran, for using up 100 million addresses without announcing them to the internet. So you're not polluting and you're actually saving.
And to Alan's credit, I think that his application for IPv6 is a perfect one, because
Yep.
it doesn't require any detailed routing. It doesn't require any global state. It's a private network, essentially.
Right. But is there really anywhere viable to go from here? Or are we just still beating our heads against the brick wall?
Well, the question is, should we bother, or should we just resign ourselves to dealing with exponential
Well, I
growth
think
of the routing system?
We've been bothering for a while and unsuccessfully.
I'm perfectly happy to go home and count all the routers that you're going to have to buy every 3 years.
Well, luckily, I'm closer to retirement than most folks here.
This is true. Alan.
It's a question that I've been asking a couple of people for the last few years now, and never really got an answer. Is there a mathematical model that look at the different routing protocols and BGP in particular, and that says what is, or is there a maximum limit in the number of routes before this thing can simply not converge?
That's a good question. I know that there had been some analysis of that back when there were problems with the rate of updates and withdrawals in the network. There was some NSF network done along those lines by, I think Craig Leibovitz did some of the analysis. It's a moving question, because it's based somewhat on CPU speed. It's based on propagation time for updates.
Let's just imagine a perfect network.
I don't know the answer.
Let's imagine a perfect network with zero time for propagation and infinite CPU speed. Okay, just perfect network. And as come on, a question for the research community: could somebody come with a model that would tell me where is the sky? Is the sky at 1 million routes? Is the sky at 10 million routes? Is there no limit? That's an information that will be really, really important if you want to have an answer to your question. That is it okay to go to this? Let's get the routing table growth.
That sounds like a fine research topic. And okay, we're going to have to cut the lines off at this point, so we'll take the last three that are at the mics. Jared?
I'm up here mostly because Ted is forcing me, sort of. Is that I said, so what alternatives do we have for BGP, or what are we doing to replace that in the long term?
For the question about BGP?
Well, if we have the existing NRLI prefix length model,
right,
how are we supposed to get away from that to something else?
That's a good question. The problem isn't really BGP, it's the amount of state you're carrying around, and inventing a new protocol isn't going to change that. Inventing a new way of propagating information doesn't change that. You need to really look at how you're designing the routing system, how you're doing your aggregation, and how completely you can be isomorphic to the topology.
Yeah,
I don't know the answer.
I think those two are potentially actually more interrelated.
Right, and again, the point of this is to determine if there's interest in actually working on a solution and in getting a community of interest together for doing that.
I think there's interest, but I think Randy's point on the operator burnout is significant, and
yep,
the challenges they're faced with dealing with the IETF and other things in the past have.
Right, And the question is, can we do something outside the IETF among the vendors, the users, and the providers that are going to have to live with this problem? And should we bother? If you're interested, send mail to the mailing list.
Yeah, I already have, but I think it's going to be hard to try and get a significant number of people involved.
I agree with you. Tony.
Tony Hain, Cisco. A couple of points that I wanted to make to your talk. The issue about end-to-end is really about identity, preservation of identity between the endpoints. That's really what that's all about. And modifying it in the middle modifies identity, right? So first order, that argues for splitting.
If endpoint IDs and locators are commingled into addresses, then certainly that is true.
And that argues for the split. At the same time, all of your security infrastructure is built around that overload and assumes that the security can know what the identity is by looking at that same locator. Okay, that's a problem. And then the other issue that I wanted to make raise was Mike Goodell was also responsible for one of the other parts of this problem, right? He was the one who set the bar that said...
Tony, we're 15 minutes over time at this point.
Just let me complete my sentence.
This argument's been going on for, what, 10 years now?
I'm not arguing against him. I'm trying to help the rest of the room understand the context, right? Okay. And Mike was also the one that said, if you're going to play and be a serious player in the game, there is one global default free zone. Back to your point, part of what we need to talk about is, does that particular assumption make sense? And that's part of the discussion we need to have. Is a single default free zone, does that make sense?
We can certainly take it up on the various mailing lists to talk about. Architecture Discuss would be a great place to discuss this, and I encourage mail to ipmh interest@external.cisco.com. Last question.
Actually, it's more of a statement than a question.
Sure.
There's a fundamental disconnect here that has existed for about as long as the IPv6 in its current form has existed, and that is the rough consensus and working code disconnect. And we've been talking about all sorts of interesting ways to do decoupling of locators and endpoint identifiers, and nobody is sending working code.
Well,
and until that time, it's flailing around.
Yes, and the point of this mailing list is to trying to rectify that problem. The fact that the domain name where the mailing list is located ends in .cisco.com suggests that there actually may be some people that are interested in prototyping some working code over this.
Where's the version identifier field for the IETF, and how do we increment it?
Randy,
Implementation details.